And okay, so hi everybody, and this week we're very happy to have Saarik, our very own Saarik, talking to us about the Earth as a transducer for dark matter, dark-photon, dark matter detection.
Yeah, it's a bit of a tongue twister. Hi everyone, thanks for coming today. So today I'm going to be talking about some recent work with Michael Fedica, Peter, and Derek Jackson Kimball on a novel mechanism to detect ultralight dark photons. So one important fact about dark photon phenomenology, which I'll be coming back to a lot today, is that in order to detect very light dark photons, you need an apparatus that's about the same sort of scale as the Compton wavelength of the dark matter you're looking at. So the lighter the dark photons you're interested in, the bigger apparatus you need. This makes it increasingly more and more difficult to.
Sorry, I still see your title slide.
Yeah.
Sorry, oh, okay, you haven't advanced yet? Okay.
Yeah, no, I was just giving a sort of like intro spiel. So the lighter dark photons you need, the larger sort of apparatus you need, which makes it increasingly difficult to do lab-based experiments as you get to very large Compton wavelengths of like thousands of kilometers or so. Increasingly, you have to start resorting to like astrophysical objects like white dwarfs or dwarf galaxies or gas clouds. But those types of objects can be very complicated. Some of their properties are very uncertain, and this can cast a lot of doubt on the bounds you get out of those. There is, however, fortunately for us, one very large object, which we are very familiar with, and we're all standing on it. It's the Earth. So today I'm going to be telling you about how you can actually use the Earth to detect dark matter, specifically as a transducer. If you, like me a month ago, don't know what a transducer means, it's just something that converts a signal from one form to another. So for our purposes, the Earth is going to be converting a dark photon signal into an observable magnetic field signal. So our apparatus is similar to those in like a cavity experiment or some sort of shielded experiment like ADMX or DM radio. In those types of experiments, you have some conducting shield, and inside you have some vacuum region. And so if you put this apparatus in some dark photon fields, if dark matter is a dark photon, then the shield will keep out all the normal photons, but it'll let the dark photons in. And what you'll end up seeing inside the vacuum is some observable magnetic field signal. And so our apparatus is very similar, except rather than using man-made shields, we're just going to be using the natural conductors that are around us. In particular, the Earth, which is below us, and above us, the ionosphere or interplanetary medium. As I'll talk to you guys about later today, these actually, for our purposes, both function as very good conductors. However, the lower atmosphere in between these, where we sit, is actually a very poor conductor for our purposes. So this will function as the vacuum. And just like the cavity scenario over here, what we're going to see is we get a magnetic field signal in between, right at the surface of the Earth. And that's something that we can detect with magnetometers. Now, it's well known that for very light dark matter, which is correspondingly high occupation numbers, you can typically treat it as a classical wave with, say, some wavelength lambda. And it turns out for these cavity experiments, which I'll be demonstrating in a bit, it turns out that if the wavelength is significantly longer than the scale of the apparatus, then you'll actually be suppressed by the ratio between the two. Or in other words, the magnetic field signal you'll see will be suppressed by m, the mass of the dark photon, times L, the size of the experiment. Now, when I say that, you might become very concerned looking over at this diagram, because you can see that in our setup, there are actually two length scales. There's the very large radius of the Earth, and then there's the much smaller height of the atmosphere. And so you might say, well, Saarik, for all I know, your signal's probably just suppressed by the smallest length scale. So maybe this is actually a tiny signal, you're never going to see it. But actually, it turns out a very important result of our work is that the signal is actually suppressed by this much larger radius of the Earth. So it actually is something that we have good sensitivity towards. So the rough outline of my talk is going to be as follows. I'm going to start off by talking about some dark photon, like a review of basic dark photon physics, and I'll be showing why we expect interesting observable effects of the dark photon near the surfaces of conductors. Next, I'll go into a little more depth on this cavity geometry that I was talking about just recently, the ADMX or DM radio scenario, and I'll show where the ML suppression in that case comes from. But I'll actually show that it's not necessarily the shortest length scale that you're suppressed by. Even in that case, you can be suppressed by a much longer length scale. Then I'll go into the Earth case. So I'll start by reviewing the conductivity properties of the various things in the vicinity of the Earth. And then I'll actually derive the signal for the Earth case, focusing on three things. One is this MR suppression that I keep going on about, that's suppressed by the radius of the Earth, not the height of the atmosphere. The second is the very particular spatial pattern of this magnetic field signal that shows up, which makes it very easy to detect because it has a very specific pattern. And then the third thing is how it's actually very robust to the details, particular details of the conductivity profile. So even if our modeling was a little bit wrong, our result is still correct and usable. And then finally, I'll get into how we actually detect this. So this is a magnetic field signal, which has some particular pattern around the surface of the Earth. So what you would want in order to detect this is some array of many magnetometers distributed all over the Earth that have possibly been taking data for many, many decades. And it actually turns out that geophysicists have been doing precisely this for their own purposes. They're interested in measuring the Earth's magnetic field. So a lot of the hard work has already been done for us. In particular, we found this data set from this SuperMAG collaboration, which has compiled many data from many magnetometers together. And we analyzed that to put a bound on dark photon parameter space. So I'll show you that bound and talk a little bit about the ways that we expect it can be improved in the future. So that's the rough outline. So I guess without further ado, let's begin. And as always, please ask many questions because I want to make sure that I'm explaining this in an understandable way. Cool. So let's get started then. So this is the dark photon Lagrangian that we're going to be working with. There are actually a few equivalent ways of writing the dark photon Lagrangian, each with their own slight little quirks. So I want to go through really quickly some of the features of the particular way we're writing it, some of those features. So first off, you can see there are two different modes. There's this A mode, which we're going to call the interacting mode. Sometimes I'll just call this the normal photon. And there's this A prime mode, which is known as the stereo mode. Sometimes I'll just call that the dark photon. And you'll notice that the interacting mode is the only mode that couples directly to E and M charges. The stereo mode does not couple to it. And this has a few important consequences. For one thing, this means that the interacting mode is going to be the only one that gets affected by conductors or other electromagnetic environments. So if you have some sort of conductor acting as a shield, the interacting photon will get blocked by it, but the stereo photon will go through and not notice it at all. The other important feature is that this means that the observable fields we're going to see are exactly the ones associated with the interacting mode. There's no contribution to observable fields from the stereo mode. So it's not like E plus a little bit of E prime, it's just E. Good. There's also a single mass term that shows up in this Lagrangian. So that means you're going to have one massless state and one massive state, in particular with a mass M. For our purposes, M will be pretty small. But importantly, these two mass states are not the interacting and the stereo modes. Because of this mixing term here, that actually it causes them to mix in space. It's similar to sort of how a neutrino mixing happens. So if you start at one point in space with, say, entirely interacting photons, and then you look at some other point in space, at that further point, they might have mixed somewhat, so you have a little bit of interacting and a little bit of stereo photons. And much like neutrino mixing, you can actually see that this mixing is proportional to the mass of the dark photon. And as you know, with neutrinos, if the mass of the neutrinos go away, then there's no sort of mixing. The the mixing isn't inherently tied to the fact that the neutrinos are massive. And the same thing happens here. So all sort of observable effects that come from mixing, we expect to be proportional to M. And so this is kind of a teaser for where this ML or MR suppressions that I keep talking about come from. So let's talk a little bit more about how this mixing works. As I said, in a vacuum, the propagation states are not exactly the same as the interacting states. So you have one propagating state which is mostly interacting and a little bit of sterile, and then you have a different propagating state which is mostly sterile and a little bit interacting. And like I said, one of these states acts as a massless state, so just like the normal photon that you're used to would, and then one of them is a massive state. Things, however, change inside a good conductor. In fact, in a good conductor, the propagation states end up aligning very closely to the interaction states. And for our intents and purposes, we're going to say they're exactly the interaction states. You can think of this again in analogy to neutrinos. If you're familiar with this, in medium, the electron neutrino, which is usually just a flavor state, actually becomes the propagation states inside a medium. And this is just because the atoms in a medium talk directly to the electron neutrino, whereas they don't talk to the muon or tau neutrino. So it's kind of singling out the electron neutrino. It's a similar thing here, where inside a good conductor, the charges in the conductor talk directly to the interacting state, but not the sterile state. So it singles it out as a propagation state. And the way that these different states propagate is very similar to how what you would sort of expect. So the interacting state propagates in the same way that a normal photon usually propagates. So it gets damped inside a conductor. And the sterile state just propagates the same way that it did in the vacuum. It just propagates as some massive state, which doesn't really care about the existence of the conductor. So kind of the picture you can have in your mind of how this works is, suppose you're deep inside some conductor near maybe some source that gives you some interacting state, some interacting mode and some sterile mode. At some other point in the conductor far away, these things will have propagated. They are the propagation states, so there will be no sort of mixing. They'll just propagate independently. And the interaction state will get damped down, but the sterile state will not be damped at all. So throughout most of the conductor, what you should expect to see is just a sterile state, no interacting state. But things change when you enter into a vacuum, because now the interacting and sterile states are no longer propagation states, so you can regenerate some of your interacting mode. And so this is why you expect, as I said before, the observable fields are those coming from the interacting mode. And so you expect some sort of observable fields near the surface of conductors, which is why the surface of conductors is an interesting place to look for dark photon effects. You can also see here why length scales become important, because essentially the more distance you have to propagate here, the more time you have to mix. And so you can regenerate more of the interacting mode. So on the last slide, we saw why the mass becomes important for physical effects. And now we're seeing why the length scale becomes important for a physical effect. So this is, again, kind of heuristically where the ML dependencies come from. Also, I guess I probably should have asked this earlier, but you guys can see my cursor, right?
Yeah, I can see the little hand.
Okay, good, yeah. Okay, great. So now we've thought a little bit about what dark photons look like in the vicinity of conductors. Let's see how this plays out in some concrete example. So let me in particular look at the cavity scenario that I talked about before in analogy to like idiom radio or something. And I'm going to take my cavity to be cylindrical. So from the side, it looks like a rectangle. From the top, it looks like a cylinder. And I'm going to suppose it's in some dark photon field, just the normal dark matter. And I want to see what type of signal do I end up getting. And as I kind of alluded to beforehand, it'll be a magnetic field signal with this MR suppression. But the important point here that I'm going to show you is that actually it's not necessarily suppressed by the shortest length scale. In fact, if I take the dark photon to be aligned with the axis of the cylinder, then it actually turns out that the length scale you get suppressed by is the transverse direction, this much longer length scale. And really the dark photon won't care at all about the longitudinal direction, even if it's much shorter. Okay, so how do we actually go about calculating things with the dark photon?
Sorry,
So,
just to ask a question at this point. If you go back a couple of slides. Yeah, so you were saying that A is damped in medium. But if you're at low enough frequencies and you have a transverse field, that's a magnetic field, which a conductor doesn't like suppress or screen or damper anything. An almost static magnetic field is just, it lets it through. So.
Okay, so this is good. So this is something I will kind of talk about a little bit later. But there's really two things that make an effective conductor, or an effective shield, I should say. One is that it has very high conductivity, but the other one is that well, actually, maybe I don't even need to explain it that way, but actually maybe there's a simpler answer, which is just if omega is very small, then this thing is very large. And so maybe it's not actually greater than sigma.
Sure, so you're just going to work in the regime where omega is large enough.
Yeah. I'm saying specifically when this is set.
Okay.
I guess the other thing I was going to say, which again I'll get back to later, is it's also about the skin depth in the material. And as you take omega smaller, then the skin depth becomes larger and larger. So if you have a material of finite size, taking omega to 0 will end up making the skin depth so long that the material doesn't look like an effective shield anymore.
Okay, yeah, I'm sure you'll talk about this stuff later. Thanks.
Yeah. Okay. Good. Great. So anyways, how do we actually start calculating things with the dark photon? So we're going to be working with this effective current approach. Basically what this means is that when we take epsilon to very small, epsilon is the mixing parameter between the two, then we can neglect back reactions. So just treat the dark photon as some constant background field. Its dynamics are not at all affected by what's happening with the normal photon. And then we can actually see that the effect of the dark photon is very similar to the effect of some sort of current. And so we can actually just treat the dark photon as some effective current. And this has a few important properties, all of which come from the fact that dark matter is non-relativistic. In particular, in this talk, I'm just going to be taking the velocity of the dark matter to be exactly 0. And so this means, for instance, there's no mu equals 0 component that we have to worry about. Everything is just in the spatial components. And in fact, the spatial components are also constant in space. So we just have some constant current field that's pointing in the same direction everywhere. And it oscillates with the frequency, with a particular frequency, which is just the dark matter mass, because again, there's no velocity. So this effective current is just some constant current throughout space that's just oscillating all together at one frequency. And then once we have this, then actually this whole thing just turns into a single photon E&M problem with some background current. So this is just a typical sort of Jackson E&M problem. A first-year grad student can do it, which is exactly what happened 3 years ago. And so even with this effective current approach, we can immediately start seeing very quickly where this MR dependence comes from just by running a simple Ampere's law argument without even really needing to do any complicated calculations. So let me consider an Amperian loop that runs along the inside of my cavity, like so. As I said before, the effect of the dark photon can be treated as like equivalent to some current. This current is actually going through the Amperian loop, so it has some current flux through the Amperian loop. And Ampere's law just tells us that that current flux has to be equal to the line integral of the magnetic field around them. And then so parametrically, we can just estimate this. The line integral would just look like the magnetic field times the radius of the cylinder. And then the current flux will look like the area, which is going to go as as r squared times the effective current, which is just epsilon m squared a. And then we can solve for what does B look like. And in fact, we see exactly what I was sort of alluding to before. We just get this MR dependence. We can, in particular, if you trade out the amplitude of the dark photon or the energy density of the dark matter, which is the thing we actually know, then one of these powers of M goes away. And so you get exactly this MR dependence that I've been talking about. B will be suppressed only by MR. There will be nothing having to do with L in any of this computation. And in particular, you can actually see that this Amperian loop could actually be placed at any point vertically in this cylinder. The dark photon basically cares nothing about the longitudinal direction in this argument. So this is sort of the basic sort of idea as to why you get suppressed by the transverse direction, but not by the longitudinal direction. So now we can go into a little bit more detail.
Can I ask a quick question about that? So your mixing is proportional to epsilon, as you've said. If I were going into a vacuum, then I would also care about basically the length that it has propagated, before I learn how much it's mixed. Yeah. Here you're in a cavity, so you're really exciting some mode. I'm struggling to understand why L doesn't enter here, like the length that it's propagated, like there's not some special point that's L/2 or something of the way down the cavity where it has mixed, the most or something like this. Is my question making sense? You're
kind of asking why, like intuitively it seems like the longitudinal direction should matter.
If this were going just from a conductor into like a vacuum, so I were just working in a half plane on, the left side is conductor, on the right side is vacuum, then would it not be true that I would measure a different magnetic field depending on how far away I am from the conductor? And this would have to do with the fact that my state starts out at the conductor purely in the sterile state, and then as I propagate away, I mix, somewhat into the visible state.
Yeah, so actually
here I don't have that, right? I'm exciting a specific mode in a cavity, so I understand it's not the same case, but I don't see why that intuition doesn't hold any water here.
Yeah, I think the thing that might be kind of intuitively confusing is that you shouldn't really think of the dark photon as moving upward in this case. It's just pointing upwards. The dark photon itself has no velocity, but like the normal photon modes that are relevant here, you can think of them as having some velocity, but that velocity would actually be transverse to the direction, right? So you should think sort of if you want to think about the direction things are moving in, you should really think about them moving in the like horizontally as opposed to vertically in this diagram.
Also, sorry, just to ask, maybe this is part of it. This will depend on r, like if we make little r the radius from the middle, the magnetic field will depend on little r.
Yeah, exactly. Yeah. So the magnetic field vanishes here, it gets larger.
Okay, so this is just because I'm looking at a transverse. Yeah, I'm okay. My intuition was coming from thinking of longitudinal, but if I'm looking at transverse, then yeah, I care about the length scale in the r direction, and there will be a spatial dependent mixing.
Oh yeah. There is some spatial dependence in this r direction. Yeah.
Okay. For a longitudinal mode, if I were looking at a longitudinal mode that was oriented in the same, this upward direction, would that depend on L?
Well, I mean, this doesn't really matter if the dark photon mode is longitudinal or transverse, because you're taking the velocity to 0. So it's going to be the same limit either way.
I think Jed is asking for if J was perpendicular to the L, is pointing in the radial direction.
Oh, sorry. You're saying if J just pointed in a different direction.
Yeah.
Oh, okay, yeah. If J pointed in a different direction, then L would be relevant.
Yeah. Okay.
But you shouldn't think of the dark photon as having any sort of, as having a velocity that goes in any direction. It just has a polarization that points in some direction.
But Saarik, you should probably clarify the last sentence you just made. L would be the suppression only if the dark photon pointed dead horizontally, obviously, as you know.
Yeah, that is true.
Any other angle, N, it's R.
Right, yeah, generically, if you took some generic direction for the dark photon, then it'll have some component in the vertical direction, some in the horizontal. So then the vertical direction will be just suppressed by R, which will dominate.
Okay, thank you.
Sorry, can you say again, what do you mean by the dark photon pointing in some direction? So what is pointing? It's K or the E prime, or?
It's the actual, like A is a vector, right? Like the dark photon has some polarization that points in some direction. So in general, or at least in our cases, A will also point in the same direction as E, the electric field, as we'll see shortly. So if that's an easier way of thinking of it, then yeah, the electric field of the dark photon.
Okay. I'm confused, but maybe go on.
Okay. Maybe if I show, maybe if I go on, it might be a little more clear. We'll see. Okay, so we can actually start talking a little more specifically about what the electric and magnetic fields look like. And in order to do that, we're basically just going to have to solve the wave equation with a current. And in particular, I'm going to do that by breaking down the electric field into two parts, which I'm going to call EDM and E response. So formally, these things are basically, in terms of differential equations, are just the specific and homogeneous solutions to the differential equation. So EDM is the thing that satisfies the wave equation with a current. E response is the thing that satisfies the wave equation without a current, such that when you add them together, they still satisfy the wave equation with a current. And usually you choose E response in order to satisfy the correct boundary conditions. So in particular, the boundary condition you're going to be looking for is that the parallel electric field vanishes. But the sort of more intuitive way you can think about this is that EDM is the field being sourced by the DM, and E response is just sort of the cavity's response to it. So the cavity sees this electric field being sourced by the DM, and it wiggles around charges in the walls of the cavity in order to try to cancel EDM at the boundary walls in order to satisfy the boundary conditions. And so in this sort of way of thinking about it, EDM is going to have some similar properties to a dark photon field, and E response will have some similar properties to a normal photon field. So for instance, EDM is going to be exactly constant in space. This is because we're taking the dark photon to be non-relativistic, and EDM is basically just going to point in the same direction as the dark photon in all places. On the other hand, E response will, like a normal photon, have some non-zero momentum. It will have some spatial variation, but in fact, this variation is going to be very slow on the scales we care about, because everything we're going to be working with is going to be sub-wavelength. So over the scales of the geometry, E response won't change too much. And additionally, another important point is that EDM will not come along with any kind of magnetic field, whereas E response will. And this is just because magnetic fields, are related to derivatives of electric fields. So since EDM is constant in space, there will be no associated magnetic field, but there will be for E response. And so that means that we're going to have some uncanceled contribution to the magnetic field, and that's ultimately what we're going to end up measuring. So what does this look like for the cavity geometry that we've been looking at so far? This EDM I've been talking about is just a constant electric field pointing in the same direction as the dark photon polarization throughout the cavity. E response, then E response is the cavity's response to it, which is meant to cancel it out at the cavity walls. But of course, it varies somewhat slowly, so there will be some uncanceled components in the middle of the cavity. So the total electric field will vanish at the walls, but it'll be small but non-zero in the middle. And then there is no magnetic field that comes along with EDM, but there is one that comes along with E response, and that's just going to be the magnetic field that we actually measure at the end of the day. And like Robert pointed out, this magnetic field that we're measuring actually does vary with radius. In particular, the total electric field, if you do it out properly, you'll actually see it's basically quadratic in this radial direction. So it'll be 0 at the walls, and it'll be largest in the middle. And since the magnetic field is just related to the derivative of the electric field, then the magnetic field is just going to go linearly. So again, we see that there should be an R dependence with the magnetic field. And this is, again, where the MR is coming from. But again, none of this calculation had anything to do with the longitudinal direction. Okay. This might be a good time to stop and ask if there are any other questions on any of this before I go into the Earth case.
Sorry, why is J effective pointing the same direction throughout space?
This is because the dark photon. So, right. So J effective is just defined as it is the dark photon times some multiplicative factor, and the dark photon we're taking to be non-relativistic. Non-relativistic really just means that it's the same throughout space. The velocity is really just how things change in space. So if you have exactly v equals 0, then that means A prime is pointing the same direction everywhere. And so therefore J also needs to be pointing the same direction everywhere. Does that explain
Sorry,
it?
I thought velocity is how things change in time, not how things change in, not how a field changes in space.
No, I mean, maybe another way of thinking of it is that like a momentum is like a spatial gradient, right? And so like the velocity is just the momentum divided by the mass.
Oh, okay, I see what you're saying. Okay.
Yeah. Okay, good question though. Any other?
Yeah, I'm a bit
questions?
confused about the E and the B field thing.
Mhm.
So you're saying that this dark photon field can be treated as just sourcing an effective current, which is uniform and slowly varying. And I would have thought if you had like a uniform non-varying current that only makes a B field and not an E field, but it's the reverse, right? You're saying it only makes an E field, then the B field is secondary. I'm just kind of confused about why.
I see. So yeah, this classification into EDM and E response, I wouldn't like put too much stock into it, like because this is really just a mathematical division. Like at the end of the day, the only thing that you can really observe is the total E field or the total B field. But yeah, I guess I think your intuition is right in the sense that yeah, if you just have a current going straight up, what you expect from that is a B field, right? By just the usual, Ampere's law thing, and that's exactly what you're seeing here. So that intuition, I think, is correct for what is actually observable at the end of it.
I see.
It's just maybe
So
not
if,
too far
if it was just pure vacuum, you wouldn't have like B is equal to 0 because B response would go to 0. Instead, there would be a non-zero B, but
No,
the
no, no.
decomposition wouldn't exist. So it just sounds weird because in the next slide you say like BDM is 0 and then there's something from the walls which gives you B response. But if you took away the walls, so there was only vacuum, you would still have B, right? Because
Only if the velocity was non-zero.
If you have a uniform current everywhere in space, there's no magnetic field, right? There's no.
But if you have a uniform current and it's oscillating, you have a oscillating charge distribution if in the sort of limit where we take it, and that's where the E field's coming from.
Yeah, I guess that's true. Yeah. Yeah. Also, to some extent, this effective current formalism only makes sense in like a finite geometry, because part of what I'm relying on is that you are contained within a wavelength. This doesn't really make as much sense if you allow yourself to go outside of the wavelength of the dark matter. Okay, good. Are there any other questions?
Yeah, so I guess I'll just ask a question about that. Let's say you actually had a zero velocity system. Would there be any cutoff as I make the scale bigger? Is the cutoff really, is the only cutoff the de Broglie wavelength?
Well, it depends on what you mean. I think
But like the magnetic field gets linearly larger as I get to larger radii. So that looks like it gets arbitrarily big. Obviously, the de Broglie wavelength will cut that off. Is there a cutoff that comes in before then? If you have,
yeah, there is a cutoff from the Compton wavelength. So I mean, really, this is not actually a linear function. It's like a Bessel function, and this is, I'm just taking the small argument approximation of that. So like it'll go linear for some amount of time, but then it'll like turn over as you go further out.
So the real cutoff is the Compton wavelength.
Yeah.
Okay.
Okay, cool. Okay, then I will now move on to talk a little bit about the Earth signal. So I've been telling you about all these interesting effects of the dark photon near conductors, but I've also told you that I'm going to talk about the Earth. So presumably there are some conductors near the Earth. So I have this nice plot that Michael has made that kind of will summarize all of the different features of the near Earth environment. But before I go into that, I want to really quickly review that actually, when we talk about something being an effective shield, as I kind of alluded to earlier, there are really two properties we should think about. One of them is what I've been mostly talking about, which is just that it has some high conductivity in the case of a conductor, or some high plasma frequency in the case of a plasma. But also there's a second thing, which is that the material has to be thick enough, right? Like a piece of tin foil isn't going to stop a lightning bolt. You need something which is thick enough that it's actually longer than whatever scale the fields damp over in the conductor. So so with that in mind, let's think about the various different layers of the Earth and above. So first off, there's the ground, the Earth itself. This acts as a very good conductor. Basically, the center of the Earth has like iron and other metals and stuff, very high conductivity. It's also very thick. In principle, this plot can go very far over to the left here. So that's actually a very good conductor. Above that, there's the lower atmosphere where we sit. This acts as a very poor conductor. And as you can see, the conductivity of this region is slightly below the mass range we care about, but certainly it's not thick enough to damp anything because the lower atmosphere itself is very small, and the damping length that's relevant in the lower atmosphere is very large because of this low conductivity. So the lower atmosphere is a bad conductor. Then there's the ionosphere, which is where things get a little bit hairy. In particular, so the ionosphere is this upper layer of the atmosphere, which is highly ionized by UV radiation. Typically, people like to think of this as a good conductor, but actually we're at such low frequencies that this is not quite true. And the reason that it gets a little complicated is because the ionosphere is actually an anisotropic conductor. In particular, it's permeated by the Earth's magnetic field, and it turns out charges like to go parallel to magnetic fields, but not perpendicular to them. So this means that the ionosphere conducts much more effectively along the Earth's magnetic field than it does in other directions. And it turns out for our purposes, the parallel conductivity is pretty large, but the perpendicular conductivity is not. And this is further complicated by day-night variations in the ionosphere, along with variations based on solar activity. So the kind of long story short is that the ionosphere is a complicated system. And I'll get back into in a sec to how exactly we deal with that. And then the last layer is the interplanetary medium. And this layer is a very good plasma, which also acts as an effective shield. It has a very high plasma frequency. So that's also good at shielding. So in summary, you have the Earth, which is a good shield, the lower atmosphere, which is a bad shield, the ionosphere, which is kind of questionable, and then the interplanetary medium, which is also a good shield.
So just to ask here, so with your sufficiently thick thing, for a conductor, you've got it depending on MA, but for a plasma, you've got it not depending on MA. Why is that?
I mean, it just ends up, so the dispersion relation for a plasma is like k squared is like omega squared minus omega p squared, right?
You need to be a bit careful. I mean, that's sort of like for things
For
above the light,
collisionless plasma.
for above the light cone. Yeah, that's. If we're looking at screening, then it's different. Right? Like magnetic fields aren't screened in a plasma again. Or they are. Rather, there's no zero frequency screening of magnetic fields in a plasma.
Oh, sure, it's zero frequency, yeah.
Yeah.
But,
so as we take MA small, then it has to go away somewhere. Anyway, but the conductor one is fine, and presumably something similar holds. I mean, something similar to the conductor thing should hold for the plasma, right?
Yeah. I think part of what might be the issue is that as you take, but like this is true for a collisionless plasma. So this is when the like ion electron collision frequencies are slower than the frequency of the actual mode. But as you take the mode frequency lower and lower, then you'll eventually go into the other limit. And in the other limit, it actually acts more like a conductor.
Yeah, exactly. So, oh no.
So then it does. Then you would have an answer that would look more like this.
A collisionless plasma. Sorry, a collisionless plasma still doesn't screen magnetic fields in the zero frequency limit though.
Oh.
Yeah, it should be like the conductor, I think. Anyway, this is probably not very important, so we're going to move on.
Okay. Yeah.
May I ask a simple question? Like, what is the rough size of sigma for seawater?
For seawater, I actually do have the paper open. So yeah, for seawater, it's actually pretty high. In terms of EV, it's like 10 to the minus 4. And I guess I haven't said yet, but the frequencies we're looking at is like 10 to the minus 17 EV or something.
Yeah. So then, like, does it matter if it rings or things like that for your?
As in, like, does it affect the lower atmosphere? Is that what you're trying to get at?
Yeah.
Yeah. So it actually turns out that the like precise conductivity of the lower atmosphere doesn't really matter. What really ends up mattering is just that there is a conductivity jump between the lower atmosphere and the ground below it. So we do in our paper like look at what happens when you even take some finite conductivity for the lower atmosphere. And yeah, really what matters is just that there's a mismatch there. It's happening. In terms of the like the like mixing effects I've been talking about, even if you go from one conductor to another conductor, the propagation states still change when you go across that boundary. And so you can still get some sort of mixing. I don't know if that kind of helps.
So, okay, maybe I will come back to this later. Yeah. Continue.
Okay.
How abrupt of a jump is it? Like, I don't know about geology, but obviously the core is very metal heavy, but like the ground that we're standing on is not very metal heavy, right? It has decreased a lot smoothly between the core and the time you get to the upper mantle. So how much of a jump is it really?
Right. Yeah. I mean, you're right that the crust itself is actually not superconductive. It's really more the lower layers that you're relying on. I guess I perhaps should have also specified that. I mean, this is kind of something if I had time, would have talked a little bit more about. But this comes back to the like robustness I had sort of alluded to earlier, where it turns out that at the end of the day, as long as you are measuring, the field somewhere where the electric field is very, very small, the argument that I'm going to give at the end of the day will play out essentially the same. So basically, as long as your entire geometry is within a wavelength, you don't expect very large electric fields to come into play.
Okay.
I think that probably doesn't make a whole lot of sense until I've talked about the argument. I will probably have to start skipping some stuff because I am running a little low on time. But okay. Yeah, the long story short of the ionosphere discussion, kind of as we've alluded to, is it is a little bit sticky of a situation. In the paper, we basically take two cases, one where we just treat the ionosphere as a good shield. And so that's our outer boundary. One where we don't treat it as a good shield and we take the interplanetary medium as our outer boundary. And kind of the conclusion we come to at the end of the day is it really doesn't matter what exactly the boundary conditions are of your problem. You end up getting the same answer at the end of the day. And hopefully maybe I'll kind of be able to allude to that slightly. For this talk, I'm just going to be taking the ionosphere as the outer boundary. So the geometry looks exactly like the picture I showed you on the very first slide. So this is kind of the geometry we'll be working with. And so really quickly, we can run through a similar sort of Ampere's law argument to what I ran through for the cylindrical cavity. And this will kind of give a rough idea of where the parametric dependence comes from and why it doesn't matter too much about the boundary conditions. So we can do a similar thing. Let's take an Amperian loop that just goes around the equator. But now let's take our Gaussian surface to be basically something that just hugs the northern hemisphere of the Earth, but it lies entirely within the air gap. Then it turns out the current, we can run the same sort of argument. The magnetic field integral along the Amperian loop will be proportional to the current that goes through the loop. And exactly the same math plays out as played out in the cavity case. And we end up seeing that we get the same MR dependence as we had there, where R is the radius of the Earth, it's not the height of the atmosphere. And you can actually visually see from this this example that the height of the atmosphere is completely irrelevant because you can take the height of the atmosphere to be as small as you want. And as long as you can fit this Amperian loop and this Gaussian surface in between the inner and outer boundaries, the argument still carries through. Likewise, you can also do whatever kind of funky things you want to the outer boundary, and none of the argument is affected by that. Basically, I guess, well, yeah, maybe let me not say that in the interest of time. I can, if people have more questions about the sort of details of the conductivity profile, we can come back to that at the end of the day. Okay. Yeah, in the interest of time, I'm going to need to go through this very quickly. So really quickly, I was going to talk about some of the different spatial shapes that can come into play in these calculations. These are given by the vector spherical harmonics, which are very similar to the usual scalar spherical harmonics that come up in the hydrogen atom and whatnot. They're indexed by the same L and M that you're used to, except now there's 3 of them rather than 1. Only the L equals 1 modes are relevant for us. And in fact, for the actual magnetic field signal that we're going to get at the end of the day, that's going to kind of look like this phi one. So really quickly, the different modes look as follows. The Y ones are always radial, so they either point outwards or inwards. The psi ones always point up longitudes, and the phi ones always point around latitudes. And what I'm showing you here is the M equals 0 ones, but the M equals plus or minus ones will look similar, but just rotated in different directions. And as I said, the ultimate magnetic field signal you get at the end of the day is going to be in this phi shape. And I will kind of jump to that really quickly. So this is roughly what the same kind of electric and magnetic field picture that I was showing you for the cavity case. I'm doing it now for the Earth case instead. And you get a similar sort of setup. You have this EDM contribution, which is exactly constant in one direction. then you get some cavity response, which is going to try to cancel out EDM, but have some very slight variations. And so there will be some slight non-zero cancellation of the E field. So the E field won't be exactly zero in the air gap, but it'll be very close to zero. And along with this comes some non-zero magnetic field. And this, the shape of this magnetic field is going to be this phi mode that I talked about. So it's going, you should think of it as going around latitudes. So ultimately, at the end of the day, the magnetic field signal has the same parametric dependence as what I showed you for the cavity case. But now it just has this very particular spatial shape that points in this phi direction. So again, think of this as like pointing around latitudes. And this spatial shape is very important because it helps us, it makes it a lot easier to detect this, because if we see any kind of fields that point, magnetic fields that point in different directions, then we know that can't be the dark photon. Okay, so let me just skip through this. A quick review of the signal properties. Yeah, as I mentioned, it's suppressed by the radius of the Earth, not the height of the atmosphere. It has this particular spatial pattern that I've been talking about. I haven't talked as much about this, but as with many dark matter signals, it's sharply peaked in frequency space because the dark matter is non-relativistic. So in frequency space, it should be very, all the frequencies you'll see will be very close to the dark matter mass. And then lastly, I didn't get to talk about this too much, but actually our result is relatively robust to the uncertainties about the conductivity profile.
So just to ask a question, one question there. For the sharply peaked in frequency thing, the fact that the conductivities of like the ionosphere and the atmosphere and things will be changing over time, how much will that smear it out?
That is a fair question. I
guess, do you rely on it being, do you rely on the 10 to the 6 thing, or does it not really matter for your purposes?
Well, I mean, it doesn't matter for the theoretical purposes. Like, obviously, you can still say
sure.
the signal
But for your
exists.
analysis.
Yeah, for the analysis, we do assume that it has a relatively long coherence time. Haven't thought too much about like if atmospheric effects would really affect that. But yeah, I guess that's a fair question.
Wow.
Okay, thanks.
I have something related. Does tide like have something to do with your signal?
The tides, like, would those affect the signal at all?
Yeah.
I
Like,
don't
does the daily
think
modulation
so,
like enter?
because yeah. Oh well. So for one thing, we're at frequencies. We're still at frequencies much above daily modulation. We're at frequencies of like minutes or hours. So I guess actually from that perspective, that also kind of answers Robert's question that it shouldn't directly affect the signal itself that you're looking at.
That's not quite right, because 10 to the 6 means that like if your thing was minutes,
yeah, I guess
it
could affect the coherence time.
Yeah,
yes.
I guess I'm saying, how much do you rely on it being like a monochromatic thing versus just like some kind of excess power?
That's the same question. Yeah, that's also my question.
I see. Okay, you're specifically worried about the coherence time. Yeah, I would have to think about that. That might be a fair point, that it might change the coherence time on shorter time scales. Yeah, that's a good point. Okay, let me try to very quickly go through the analysis. Yeah, so as I mentioned before, this is a magnetic field signal at the Earth's surface, which has some particular spatial pattern that we want to look for. So ideally what we want is some collection of magnetometers dispersed over the Earth. And it turns out that actually geophysicists have provided us with precisely that. We've particularly been working with this data from the SuperMAG collaboration, which has over 500 ground-based magnetometers, been taking data since 1970, and it comes with this 1-minute time resolution. There are some properties of the data set that make it a little like difficult to deal with, such as the number of active stations at any given time varies a lot. We've plotted here the number of stations over time, and you can see it changes over the course of the data set by a significant amount, but even like from 1 minute to the next, it changes quite a bit. And that makes the analysis a little bit tricky, but we found ways of dealing with it. In the interest of time, I probably won't really talk about the analysis. I'll just get into what the results look like. So this right here is our limit curve. What I've also plotted is some various astro bounds. Most of these are heating bounds from various things like dwarf galaxies or gas clouds, things like this. You'll notice that all of these lines are exactly parallel. This is because of the typical mass suppression that I've been saying is sort of comes in for all dark photon effects. That causes all of these effects to go precisely inversely proportional to the coupling epsilon. You can see that our curve actually slightly beats this, or at least goes faster than this though. That's because in addition to the mass suppression, we also have the additional effect of 1 over F noise. So as you go to higher and higher frequencies, your noise gets smaller and smaller. So we actually go up faster than just as M. You can see we end up getting cut off here. That's simply because of the 1 minute time resolution that I mentioned earlier. And so if you had data which took measurements at higher frequency, then you would be able to actually go even further. And one might even expect you might be able to beat some of these astro bounds as you go further to the right on this plot. And as it actually turns out, SuperMAG has such data. They're releasing 1 second resolution data as we speak. And if the trends continue, then our limit should get even better and better relative to these astro bounds. So we look forward to improving our limits in that sense. There are also various other ways we could improve them. Perhaps try and actually model some of the magnetic field of the Earth. We really just took an agnostic stance and didn't try to model anything in our analysis. Maybe some better analysis techniques, better magnetometers, or even more data might be able to help. So in summary, I talked about a novel way to probe ultralight dark matter using the Earth as your transducer. It takes advantage of the natural conductors that are here around us. Importantly, our signal is not suppressed by the height of the atmosphere. And so this leads to a much larger signal than you might have naively expected. It's both coherent spatially and temporally, and robust to the exact details of the environment. And finally, we were able to set bounds on parameter space, but this is only the beginning. We expect that you could maybe even improve these bounds further. So thank you. And any final questions?
Okay, well, thanks very much. No, that was a plain to talk. Do we get any further questions?
What's the optimistic, if you guys are thinking about the future of what could be done with such a technique? I mean, there's going to be 1 second data coming out of this SuperMAG collaboration, you said. Can you do much better than that? Is it realistic experimentally to do better than that?
I think certainly you could take more frequent data. You can also get much better magnetometers. Like the magnetometers that the geophysicists are using are not necessarily that good because the Earth's magnetic field is pretty large. It's not that hard to measure. It's unclear whether or not the magnetometers would actually get you a better bound or not, but certainly you could get better magnetometers. Definitely, I think you could do higher frequency measurements too. It's more just a question of how much data you could get. One of the big advantages of SuperMAG was that it was just such a large data set. So it would just be a question of if you can get that same amount of data at higher frequencies. But obviously, if you're measuring at a faster cadence, then it takes less time to get that data. So I think even setting up some smaller number of stations at higher frequency for a shorter amount of time might be able to get you comparable sensitivities, but go to high frequencies.
How many stations do you need to extract the signal well? Like, is the number of stations contributing in a significant way to your noise floor here? Like,
I
because you have
mean-
to average out, so the signal you're looking for is small compared to the Earth's magnetic field, right? So presumably you're relying on the fact that you have some spherical harmonic signal that the Earth's magnetic field shouldn't be in.
Yeah, exactly. So the more stations you have, the more you'll suppress the noise. Like just randomly getting noise in this particular spherical harmonic, that'll go down the more stations you have, versus your signal won't. So yeah, the number of stations does still help. It probably helps like root n or something like that.
Kelly, do you have a question?
Yeah. Well, like I'm wondering, like coming back to the rain part, like where I was asking about like the weather. Like, will you be able to use like some data like when it's raining? Like, does it like matter? Like, does it change the like conductivity enough?
Well, do you mean, does it like change the actual signal, or does it change the coherence time of the signal, or does it change the noise?
Should I think of it as a changing of boundary conditions when it rains? Because like if I like you are saying like what I understand is the calculation like you do like requires it is like basically like vacuum like for 2 pi r, right? Like but like now like if I'm raining like let's say like in Britain, does it contribute as a point like a defect for like your detector?
Yeah, so you can think of it as changing a boundary condition, but like I said, that the signal itself doesn't actually depend on the boundary conditions. I guess, let me see if there's kind of an easy way to explain this. I mean, as long as basically this surface exists, right, you can run this sort of Amperian loop argument. So it doesn't really depend on the complicated details of your boundary conditions.
So you're saying like if I change the like a topology of like the conductivity, like it doesn't change things.
Yeah.
I mean,
That sounds strange.
let's say that we surrounded our detector with enough thickness of a good enough conductor that it was screened, that it was like less than that the thing is thickness is more than the screen depth. Then that detector would presumably not see a signal. I think Curly's maybe asking if you have it, if it's in a rain cloud, like if you've got a big rain cloud in your city, is the skin depth set by that kind of thing sufficiently small that it would mess with the signal at a magnetometer?
Yeah, that's one part of the question. Yeah.
I see.
Can we trust data from like Robert's hometown?
It rains a lot. I mean, and more generally, just like what are the noise sources in?
Yeah.
Do you know what the dominant noise sources in the data are?
I mean, no, we're not sure specifically what the noise sources are. There are some like correlated noise sources between stations, so it's not just local things. Yeah, I guess I'm not sure even like how strong of a conductor like a rain cloud would be. I mean, that's not something we looked into in particular. But like a rain cloud's not like that large, right? So I don't know. It's not clear that it would actually screen any charges in any significant way.
I mean, by the number, like what's for the numbers that you're talking about, like what's the screening length in, say, the ionosphere for the masses that you're talking about?
In the ionosphere?
So like if we take, just to give like for a good, your best conductor is the ionosphere or something, right?
Yeah.
So what's the screening length there for the masses that you're talking about?
Let's see. I think it's roughly like a couple kilometers.
Yeah, so in that case, unless atmospheric features have a much higher conductivity than that, then the screening length is probably too large to be relevant, I guess.
Yeah.
Solid ground.
So on the screening depth thing then, so this is a separate question. If you went to lower masses, the screening length would become even larger.
Yeah, I think that's what
Uh,
Michael.
Yeah.
And at some point, like the ionosphere and things would stop being a good shield.
Oh yeah, yeah. So that
No.
then you're in the regime where like the interplanetary.
Yeah, I'm saying, but I mean, so that, but you might get a bigger signal because the scale of your homogeneities might be to do with like stuff happening in the solar system. So is this something you've looked at? Like if you go to even smaller masses, can you win by the fact that you're now sourcing your field from inhomogeneities on larger scales?
So I mean, this might go back to the question you were asking about this damping length.
Yeah, exactly.
Because I think, I mean, I guess it depends. Like if this damping length is indeed just the inverse of the plasma frequency, then it doesn't matter how low down you go.
Sure. But that can't be true, right?
Well, certainly if you go below like the collision frequency of the plasma, then you're no longer in the limit where it's acting as a collisionless plasma. But I think in that limit, it starts to act like a conductor.
But even no, even
but
conductors don't screen. Even a conductor doesn't screen magnetic fields at low enough frequencies.
Right. Yeah. So sorry. You're right. So yeah, in that case, it will go over to something more like this, where it actually will the damping length will get longer as you go.
Yeah, exactly.
Yes. Okay. Sorry. That's fair. However, the like collision frequency is something like 10 to the minus 20 eV or something like that. So you're already up against the like fuzzy dark matter bound for dark matter. Like you can't go much below that.
Yeah, maybe there's just not enough space to win very much. That's plausible.
Yeah.
Can I ask about you've shown there's been a bunch of questions about boundary conditions, and you keep showing this picture with the Gaussian surface and the Amperian loop.
Mm-hmm.
And the thing that's confusing, so I think what I'm supposed to read off of this is a parametric estimate for how large the B field should be. Yep. And I should see that this parametrically goes as R. That's fine. But when we want to go and detect this, you're going to be looking to tease out a very specific spherical harmonic from the data set, right? So you are going to rely on the spatial geometry of this B field, which seems like it could be sensitive to things like, you know, point defects in your conducting surface, or you know, weird inhomogeneities of whether you have the ionosphere versus the interplanetary medium or things like this. Why is that not the case?
Yeah, I mean, so this argument, like you said, is really just to give you a parametric dependence. Yeah, in order to actually figure out the spatial dependence, you have to go into a little bit more detail. I guess I can try to kind of explain basically, hopefully this whole story of like what the electric and magnetic fields are doing kind of made sense, in the sense that you have some electric fields from the dark matter, and then they are basically canceling it by some cavity response. And then you get some leftover magnetic field, which corresponds to that cavity response. So the basic idea here is that basically, regardless of what the boundary conditions exactly are, this cavity response will, to leading order, cancel out the EDM, regardless of where exactly the boundaries are, because E response is varying so slowly that it basically looks like it's pointing downwards everywhere. So essentially, this is the correct answer to leading order, basically regardless of what the boundary conditions are. And so you can find that actually this B field is also the correct answer to leading order. It's the correct answer specifically for the phi modes. Other modes can change as you change the boundary conditions, but if you're specifically looking at the phi modes, then the boundary conditions don't matter. I don't know, did that kind of make sense?
Is the following statement accurate? That if you have some weird change to the geometry of the conducting surface, you will change the spatial structure of the magnetic field. You will have other spherical harmonics that may pick up power, but you shouldn't adjust the fundamental spherical harmonic by more than, like, I don't know, order 1 or something. Like you might have a tiny decrease, but
Well, yes, you can have other ones show up, but in fact, this one will not change. Like this particular one that we're looking for.
to
will not
leading
change.
order.
Yeah, to leading order.
Leading order in what?
In MR.
In MR. Okay.
Can I ask one?
Sorry, I was just gonna ask, is that why you're only interested in L equal 1? Because it doesn't change?
I mean, that's also in the exactly spherical case, that is the only mode that ends up getting sourced. But yeah, in the other cases, that's like the leading order
Okay, thank you.
contribution. Yeah, Alexander, were you gonna ask something?
Yeah. So, you considered dark photon signals. Did you also think about similar signals from different kind of ultralight dark matter, like axion type?
Good, very good question. So, oh, maybe I should have put that in the slide. But yes, we actually we actually somebody reached out to us earlier in the year, specifically asking about this, and so we have been talking to one particular guy. His name is Ariel Arza. Also trying to think about how you might be able to do this with axions too. In that case, you actually need to you need to have a magnetic field to convert the axion in, but the Earth itself has a magnetic field, so you can use that
exactly.
magnetic field. So,
So,
that is another interesting future work. Yeah.
So okay, so does it work out that like the multi-Tesla B times meter is like competitive, is on the same order of Earth magnetic field times like 1,000 kilometer or something? Is that the idea?
You're saying how does this translate to
saying,
like the axion case?
Oh yeah, I'm just saying. So like the Earth magnetic field is what exactly is it again? Can't quite remember the numbers.
It's like micro Tesla-ish. I think it's,
okay, so yeah,
I think it's like Gauss-ish.
Fair enough. So then it does actually, maybe that, yeah, you need to work out how the scaling is. I'd have thought that the signal power though, I'd have thought it would scale as like, yeah, okay, fair enough. There's probably there might be a squared there. Okay, sorry, talking to myself.
Yeah, we did a very rough back of the envelope estimate, and I think it was like coming around near cast bounds, but we'd probably have to look again to be sure.
Cool. Okay. Yeah. Any other questions? All right. Well, if not, then thanks, Saarik, again, and thank you very much for a nice talk.
All right. Thanks, guys.